Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss another one concept of viscous resistance of footstep bearing. In our last lecture, already we discussed regarding one viscous resistance of journal bearing. So here we are going to discuss about the footstep bearing. So in the footstep bearing, the shaft is located in vertical position. Okay, so this is the shaft and this is the bearing part, and between the shaft and the bearing we have a liquid which is known as oil. So a oil film is there, okay, in between the shaft and the bearing, okay, which will reduce the wear and tear between this when it is rotated. So to reduce the wear and tear, oil film is given here. Now the resistance or the viscous resistance, we can say, which is offered by the oil to the shaft, okay, what is going to affect? Now, the radius of this shaft is going to be affected by the viscous resistance provided by the oil, okay. But in a previous case, in the previous video, if you see that that is journal bearing, I'm talking about the journal bearing. In the journal bearing, the shaft is located like this, okay. If you have seen the video, you can understand the shaft is located like this, okay, and the bearing is in this way, it is given, and between this shaft and the bearing, here also oil film is there, okay, and this oil film is provided to reduce the wear and tear and for a better movement of this shaft, okay. Now here also that bearing is also fixed. So why I'm showing this one? For a better clarification of this footstep bearing and the journal bearing. So this diagram is regarding the journal bearing, and this is for the footstep bearing. So here footstep bearing, the shaft is located vertically, okay, yeah, and this is our bearing part which is fixed, okay. In between this, the oil film layer is there to reduce the wear and tear. And now if you see journal bearing, we have the contact of this surface. Which contact? Now with respect to this oil film, the surface contact is there, but while coming to this footstep bearing, we have the contact with this radius part, or we can say the diameter part of this shaft is coming in contact of this oil film. So for this case, so the viscous resistance for this footstep bearing, okay, can be calculated by considering the small elemental circular ring, okay. Small elemental circular ring need to be considered, and which is with a radius of r and the thickness of dr, okay. So which elemental radius I am talking? Now suppose this is the diameter of this shaft and a small elemental strip, suppose in between you can consider a small area. So here the small elemental strip, what we considered here, this one, this part, so which is located with a radius of r, okay. A small radius of r I can consider here. Suppose this is the small elemental strip and the thickness of that is dr. Suppose this area, one small area we have considered. So for this we need to consider, okay. So this one not exactly like this, I'm showing just for this diameter, I'm showing this one, this length, okay, where I have taken. So a small circular elemental strip ring need to be considered to identify the viscous resistance for that, and what is the power absorbed in this rotation, that also can be calculated. So to calculate that one, what are the parameters need to be considered? One thing, first one is we can consider the viscosity of the oil need to be considered, first things. Second thing is what is the rotation, or you can say the speed of the shaft. This is viscosity of the oil which is provided here, and next is speed of the shaft, and next the thickness between this shaft and the bearing, that is small t, and one more is the radius of this shaft also can be considered. So these are the parameters will be considered for identifying this viscous resistance, or you can say the power absorbed by this, okay. And first of all, we need to calculate the area of the first of all, we can calculate area of the elemental ring. Area of the elemental ring. This ring is nothing but this one. Okay, we are talking about this ring. Okay, now this ring is situated from this point to radius r and with a thickness of dr. So that also there, but that is not the parameter. That is the location, radius r and thickness dr. So to find out the area of the ring, we can write, we can denote this one as a dA. Small part is there, that's why dA we can consider. And for this we can write, this is 2 pi r dr. This is the thickness, radius of r. And this one we can give a equation 1. Okay, now first I have calculated the area of the part. Now, though there is a movement is there, like there is a rotation is there of the shaft. Okay, so now we can consider a concept of Newton's law of viscosity to identify the shear stress. So we can write the shear stress from the principle of Newton's law of viscosity. We can write tau equal to mu into du by dy or del u by del y. We can write, so du by dy also you can write, no issue. Now here this mu equal to mu into du by dy is nothing but in that case, like Newton's law of viscosity case, we have taken du equal to the change in velocity, and this is the change in height or thickness also. For this case, what we can consider, we can write, suppose du is there, this is change in velocity. So here in this case, change in velocity is nothing but what I can write, suppose initial velocity v and final velocity v, again v1 v2. So there is no final velocity, no initial velocity, only one velocity which is present here, that is called tangential velocity need to be considered. So that is v actually. So v minus 0. So we can write only v. Okay, and dy is nothing but the change in height or change in thickness. In this case, the change in thickness or change in height is nothing, that means the distance between the shaft and the bearing. So that is with a thickness of t. So because this is the t is also the oil film thickness. So that is nothing but in place of t dy we can write t. Okay, and this v, actually this is tangential velocity as I told. Okay, this tangential velocity for what? For this elemental string. So for this elemental string of this, that means it is situated with a distance of r. Correct. So this velocity or tangential velocity of the shaft with a radius of r can be calculated, or I can write like this. This is v equal to, I can write omega into r. Okay, so this one again, omega into r, I can write 2 pi n by 60 into r. Okay, so this also I can write. Next, this is about the velocity. Just put all this value in this equation. I can give equation 2 because equation 1 already we have given. So this one, just put the value of all these things. So tau equal to mu into du. Du is nothing but v, and this is dy. dy is nothing but t. Okay, so this is about the shear stress. Now, why I calculated the shear stress? From that I can identify the value of shear force. So now you can write the shear force on this ring, on the elemental ring which is there. We can write the shear force on the ring is nothing but, we can write dF equal to tau into dA. So this is nothing but how we got, you can say. So we know that shear stress equal to shear force by area. So here the force which we are considering for this very small one. So I can write dF by area also small one. So dA. So dF equal to tau into dA. Okay. Now tau value already we got here. That is nothing but mu into v by t into area. Area is nothing but here 2 pi r dr. Okay, now again I can write this one df equal to, I can write this all this value mu V value how much? This one, 2 pi n r by 60 into, this is V value, again we'll get 2 pi r dr. So 2 to 4, 4 it will be going to be cancelled. Again V by t is there, so write t value here, and so all the things if you multiply, finally we are going to get, so this is mu by 15t, mu by 15t, and here it's there pi into pi, that is pi square, and also you can write this is r square is there, again n is there, and dr is there. So these are the value for the shear force. Okay, now this one we can give equation 3, shear force equation. See, one by one step I'm doing. First shear stress, next shear force. Why I calculate the shear force? So that I can calculate the torque required for the viscous resistance. So next what I can write? Now I can write torque. The torque required to overcome the viscous resistance. So here also I can write dt equal to, so torque is nothing but the force applied with a distance. So distance is nothing but r. We are talking about the small elemental area or small elemental ring, what we have considered, for that only I'm writing. So df already I have written the value, mu by pi 15t pi square r square n dr. So again one of r is going to be multiplied in that. So finally what we are going to get here again, so we can write mu by 15t pi square n r square into r, again it is going to be r cube into dr. So this is the torque required to overcome the viscous resistance. Okay, now we need to find out the total torque. Now we need to find out the total torque required to overcome the viscous resistance. Total torque required to overcome the viscous resistance. Required to overcome the viscous resistance. Okay, so for that what I will do, I'll just integrate this equation, this torque with respect to from 0 to with a distance of r. Okay, so what I can write here, t equal to, I can write integration of dt, that is 0 to r. So again 0 to r, what is the value was there, mu by 15t, mu by 15t, here it is pi square n r cube dr, pi square n r cube dr. Okay, so this is the value of dt. So now we need to just integrate this equation. So if you are going to integrate this equation, just this constant terms we can take it to outside. So that is nothing but mu by 15t pi square n. So integration of 0 to r cube dr. So this is going to be integrated. So what we are going to get, again mu by 15t, pi square is there, n is there. Now r cube dr. So r cube integration of r cube dr is nothing but r to the power 4 by 4. So I can write here r to the power 4 by 4, 0 to r. So 25 square. Okay. Next what we are going to get from this, we'll get the value. Finally I can write the same line, I can just let it write mu by 15t pi square n, and this is r to the power 4 by 4, because this is 0 is there, so nothing will come here. So finally what we are going to get, mu by 15t pi square n r to the power 4 by r. So this is the torque value. So this is the torque value. So equation we have given 3. Now this one we can give equation 4. Now our requirement is, what is the power absorbed? What is the power absorbed? So this one, what we can write, as we know, the formula for this P equal to 2 pi nt by 60. This one also you can write this is 15 is there, again 4 is there, so we can multiply, we can write 60 also. Anyway, P equal to 2 pi nt by 60. So actually, to identify this power, we have done this much. Torque we have identified. For before torque we have identified the force, shear force, then before shear force we have identified the shear stress. Okay, so this is the formula for this. Now just put this value of torque in this equation. You can write P equal to 2 pi n, T value this one. So T value you can write mu pi square n r to the power 4 divided by 15 T into 4 again into 60 is there. Okay, so this is all total. Now what I'll do, I'll just multiply everything and let's divide this all the things. So this 2 is there, again here 4, so 2 we can write. So 2 into this 15 is there, so we can write in the top numerator what are the points will be there. Now pi, again pi square is there, so it will be pi cube n, you can write n square, mu is there already, so mu pi cube n square r to the power 4 divided by 60 into 30 T. So this is about the power. So if you see, what are the terms are there? Mu is there, n is there, r is there, t is there. So these are the parameters which is involved in this. I told in the starting. Let's correlate with this, and this is the final equation. We can give it equation number 5. This is the equation number 5. What is the power absorbed? Mu pi cube n square and r to the 4 divided by 60 into 30 T. Okay, let's go back to the starting one. So let me highlight what are the points we have discussed here. Now see, while calculating the viscous resistance of this footstep bearing, these are the parameters we have considered, correct? As I told, what are the viscosity of this oil film which is used here, and what is the rotation of this shaft, and the thickness between this shaft and the bearing. This one, this is the shaft position, this is the bearing position. So what is the thickness of this between this, or you can say the thickness of the oil, and the radius of the shaft which is provided. So these are the parameters which are involved in this. And finally, if you see, we got mu, n, r, and t. And this pi value as usual came because we have taken the area part. Now first we have started from the area, dA equal to 2 pi r dr. Then we came to the Newton's law of viscosity, tau, which is equal to mu into du by dy. Then we came to again shear force. Once shear stress calculated, we have calculated the shear force. What is the shear force acted on the small elemental ring? Then after that, again we went for the torque. What is the torque required to overcome the viscous resistance of that? Then finally, once torque calculated, this is for the only small elemental area torque. Then again, we need to find out the total torque required to overcome the viscous resistance. So just integrate of this one. After that, the power absorbed P equal to 2 pi nt by 60. So I hope you understand this derivation. If you are having any kind of query or doubt regarding this, you can give a comment on the comment box. Thank you all.